start out section 11.3 with a little bit of a question for you. A choice, a preference. I'll give you a choice of $1 million or, for the first day of a month, I'll give you a penny. On the next day, I'll give you 2 pennies, then 4, and then 8. And look, by the end of the week, you're making 64 cents. So I'll do that for an entire month. Which would you rather have, $1 million or the sum of all these amounts? $1 million, sum, $1 million. Pretty easy, $1 million, right? If you go for a month, so we'll call it 30 days. So yeah, so a little bit short if you're thinking of October or something like that. But it actually turns out that you are much better off with this. How much better off? After 1 month, you'd be the proud owner of $10,737,418.23. That's for 1 month. Starting out with a penny. You double it every... Yeah, so the next one is going to be $2.56, and so on. Wait a minute. I just told you all this. I said, so, next day is 4, 8. I was kind of thinking that you saw the pattern, but maybe I'm guilty on that one. Yeah. All right. So, this astounding total is a result of something called an exponential function. And that's what we're going to look at. In fact, we'll look at the exponential function that you would relate to this, which would be on this handout here. So let's talk about that. Exponential functions are a class of functions that have this kind of a shape or this kind of a form to them. B to the x. Now, for my convenience, I'm going to restrict b to be greater than 0 and different than 1. Actually, we'll probably just work with b greater than 1, but it has to be greater than 0 and different than 1. That's your generic exponential function. So, okay, below that, I've got 2 examples of functions, and I'd like you to tell me which one's the exponential function and which one's not. So is it f of x that's the exponential function, or is it g of x that's the exponential function? F of x, good. So with an exponential function, you've got a fixed number raised to a variable power. That's an exponential function. That's where this class of function gets its name, is that the variable's in the exponent. Now to get familiar with these, let's do something. Let's plot some points. So g of x is x squared, and f of x is 2 to the x. Let's first of all see what points we'll be plotting if we're plotting g of x as opposed to f of x. So 0 squared is 0, 1 squared is 1, then 4. And I hope these are easy, right? 5 squared, 25. 10 squared is 100. How about 20? Can anyone do 20 in their head? 400. Well done. Well done. Now with 2 to a some power, it gets a little bit more challenging. So for instance, 2 to the 0 power, or anything to the 0 power. 1. Good. Something to the 0 power gives you 1. 2 to the first power, of course, is just 2. How about 2 squared? 4. Can anyone in their head do 2 to the 5th power? Can anyone do that with their calculator? 32. Excellent. Now, if you square this, or square this, and get 2 to the 10th power, which is kind of surprising, because up till now, these numbers, 1 and 0, 1 and 2, 4 and 4, 32 and 25, they seem pretty similar. But 2 to the 10th power is 1,024. Wow, that's a big jump. And 2 to the 20th power? 2 to the 20th power, I'm going to use all the room I've got here, 1,048,576. Wow. What's going on there? It's really taking off. This graph is getting very big very, very quickly. So what I want you to do is I want you to look at these 2 functions and I'm going to color them different, here and here, and decide which one of them is which in the graph below that t-table. So try and decide, well, which one of them is the exponential function, which one am I going to graph with the orange, and which one's the graph of a parabola, which I'll graph with the pink. Well, I hope you get an educated guess, right? Because we just came up with a t-table showing all the points, right? So you know that 20 goes with 400. Yeah. Thanks, Chris. So this one, the one that's kind of farther out, that's your f of x. That one's growing a little bit slower than the other one. So let's see. I'll draw it like this. So that's my f of x. And this one, that's my exponential function. So, wow. That's kind of...
What is the one that strikes slow?
It is g of x. Oh, I'm sorry. I said f of x. Well, this is f of x, and this one's g of x. So if I misspoke, my bad. So this is y equals f of x, and this is y equals g of x. The thing you should see, and the thing that I'm trying to stress here, is that the exponential function grows really, really quickly. And maybe it'll help to put a little bit more emphasis on that fact here. And let's do that with the aid of a quick PowerPoint. Now on the graph on the side of the projector, I've got a little room to draw some things. So let me put that first point up there. And I've got everything scaled in terms of centimeters. So at 5 centimeters on the x-axis, I'm going to draw 32 centimeters on the y-axis. Here's 5, 10, 20, 30, 40, 50, 60, 70. Now, like I said, this is really the only point that I'm going to plot, because this function grows really, really quickly. 32 centimeters. 32 centimeters is about the distance from, say, a skier's elbow to the ground. So something like that, about 32 centimeters. How about the next point? 2 to the 10th, 1,024 centimeters. That's about 30-some feet. That's about the distance from the sidewalk on Lincoln to, I don't know, the top of the parking structure across the street. 1,024 centimeters. Let's keep going. 20 centimeters along the x-axis, over 1 million on the y-axis. Now, if you wanted to plot that point at x equals 20, well, you'd have to jump on a plane, all right, because that's over 6 miles high. Yeah, Shamu, yeah. This plane, I think this is the one that they use to fly between Phoenix and San Diego. That's the one they use there. 35.16. So to plot that point that you can easily see on the x-axis, you need to go up 239,000 miles. And, of course, if you go in the right direction, you might land on the moon. Yeah. Are you getting the idea that this function grows really, really quickly? I mean, that plot that I can easily reach from x equals 0, reach out to graph 43.7. Wow. Now you're going to land on the sun. Hope you bring some screen, you know. So you're going to get warm. And the last one, this is also the sun. There's just some cool pictures. The last one, you'd have to travel over 4 light years away to graph that one. So that would put you at Proxima Centauri, the nearest star to ours. So anyways, it grows really, really quickly, and that's one of the conclusions that I want you to know about this function, is that the graph grows really, really quickly. So the exponential function grows really quickly. So that's one conclusion that I want you to get out of this handout. But let's move over to this other graph and this other t-table and fill it in to try and understand some more about our exponential function. So over here, I'm still going to be working with x squared, but this time I'm working with negative values for x. So 0 squared, negative 1 squared, negative 2 squared, negative 3 squared, negative 4 squared. And the nice thing about your your parabolic function, that is y equals x squared, is that it doesn't matter if you square something negative or positive. You're still going to get something nice and positive. You get nice symmetric points here. How about 2 to the x? Well, 2 to the 0 we already know, that's 1. How about 2 to the negative first power? Nice. Remember, you take the reciprocal and get rid of that exponent. So 1 over 2, 1/2, thank you. 2 to the negative second. What's that one going to equal? 1 over 4. Because it's going to be 1 over 2 squared, but 2 squared is 4. Well, let's keep going. We only got 2 more points. Let's finish it out. 2 to the negative third, 2 to the negative fourth. What are these last two going to be here? 1 over 8, well done. And 1 over 16. Do you see a little bit of a trend in here? You know, 1, 1/2, 1/4, 1/8, 1/16. What are these numbers getting close to but never will actually touch? 0. They're getting closer and closer and closer to 0. And you can see that when you look at the graphs here. So this one, the one that gets close to the x-axis but never touches it, that's our graph of f of x. So to the left of this point, to the left of the y-axis, it gets close to but never quite touches the x-axis. And that's another conclusion that I want from you. I want you to know that the graph of the exponential gets close to the x-axis, which is also known as y equals 0, but never touches it. Now, in fancy mathematics terms, this line here that the graph gets close to and never touches, that's called the horizontal asymptote. So y equals 0 is our asymptote. And that's going to become important for us on the flip side of this handout. There we go. So y equals 0. There's one more thing that I want us to notice about the graph of the exponential. And we've actually seen it a couple times. Let me share it with you in general. Our exponential function is going to look like this. F of x is b to the x. That's the generic exponential function. Can someone remind me how I find the y-intercept of a graph? What do you do to find the y-intercept of a graph? Yeah, you set x equal to 0. Well done. Thank you. So what's b to the 0 power? Which one? 1 or b? 1. Anything to the 0 power is 1. So what I'm saying is that this graph is always, always, always going to pass through the point 0, 1. So passes through 0, 1. And that's the last of these 3 features of the graph of an exponential that I want you to be familiar with. Is that it's always going to pass through that point. And we saw it. We saw it on both tables here. And you can see it from the graph right there. This passes through 0, 1. So let's flip things over here on our graph, or excuse me, on our handout, and take a look at the graph of 2 to the x. What should I provide it here? So this is the graph of y equals 2 to the x. But I want to tweak that a little bit. What if instead of looking at y equals 2 to the x, what if I looked at y equals 2 to the x plus 3? Is that graph going to look wildly different than our other graph, or is it going to be shifted somehow? Shifted. Should be shifted. Now you've got 4 choices, right? Up, down, left, and right. Which way do you think it's going to be shifted? Up 3? Right 3? Left 3? All right, we got all. Do I have anyone for down 3? That'll complete the 4 points of the compass. All right, left 3? All right, well, let's take a look here. So here's your point at 0, 1. Let's take a look at this graph. Got shifted to the left 3. And you can see that. You get that point there at -3 and 1. So, okay, let's go back to our little handout. This is going to be shifted to the left by 3. Yeah, that's the thing with horizontal shifts, is that they tend to seem in the opposite direction. Like, wait a minute, shouldn't that be to the right 3? And let me talk about that, because that's a good question. So let's see, 1, 2, and 3. Now, I get this point right here at 0, 1, because when I put in a 0 for x, 2 to the 0 power is 1 for y, right? So you're comfortable with that part? Let's come over to here in this exponent. What value of x would I put in here so that when I add that value plus 3, I get x equals 0. I get a 0 for the exponent. -3. So the point that was here now happens here at -3. So it's a great question, and I hope the answer makes sense to you. Yeah, but in general, in this class, our horizontal shifts has always been opposite of what the sign suggests to us. Let's do ourselves one more favor to make this graph a little bit easier to draw, and that is, let's plot the y-intercept. How do you find the y-intercept of a graph? Set x equal to 0. All right, so somebody tell me, if I put in a 0 here, 2 to the 0 plus 3, what would that give me for y? You're supposed to make me look good. 8, yeah. 0 plus 3 is 3. 2 cubed is 8, which you can get from the left-hand side board or from your calculator, or you can just calculate it. But 0 and 8. So that point would be up here. And then we'll play a college-educated version of connect the dots. Here, I'm going to kind of move this to help out myself anyways. Maybe not you. Maybe you're getting vertigo. Sure, I'm not sure. But there we go. So something like that. Nice. It's nice if you draw that y-intercept. You don't have to, but I appreciate it, and occasionally I give extra credit for it. Are we okay with that one? All right. Great question. It never quite touches the x-axis. It always stays just a little bit above it. So when you draw it, try and come close. If you accidentally touch it or something like that, that's fine. The only thing that I ask is that you not egregiously go under it. And then the other thing that happens to people sometimes is that occasionally they'll want to like ricochet back off of it, like, ooh, I don't want to touch it. And then they come up and draw something like a parabola. So, I mean, those are the only times that I'll take a little bit off. But, if you do a reasonable job of getting close to it, that's fine. That's all I'm looking for. Let's try another one similar to that. I appreciate the questions there. Is there another one? Okay. So the next question or the next graph would be y equals 2 to the x minus 2. How do you suppose this one's going to be shifted? To the right by 2. Good. So again, this is going to be a horizontal shift And because I have a -2 there and horizontal shifts go opposite that, that's going to be to the right 2. This point right here, the one that I tell you to keep track of, 0, 1, that's what you should work with. Say, okay, if I shift 2 to the right, then I have a point there at 2 and 1. And from there, you can draw your graph. Just do your best to try and mimic what's here. I tend to give you this example right on your test. So all you have to do is say, okay, this has been shifted to the right by 2. On a test, I'll give you equations and ask, so I'll give you stuff like this. Now there's going to be a little bit more we're going to do with these things, but this is the general idea. I want you to be able to look at something and tell me, all right, this is how the graph has been shifted. Well, we didn't find that here. You could, if you put in a 0, you get 2 to the -2, which is 1/4. And you can kind of see that, I'm not too far off of that. If you really wanted to find that point, you could. 0 and 1/4. It's hard though on this scale because you're really trying to graph something that's pretty small. So, like I said earlier, sometimes I give extra credit for graphing that point. But if it's a fraction, I'm not going to worry about it. I'm not going to ask that you worry about it either. Just do your best to draw something like this. Okay, we're looking all right with these first two? Not bad? Jack, you hanging in there? Thank you. All right. Let's try a different one. Let's try y equals 2 to the x minus 3. How do you think this graph's going to shift? Down 3, up 3. Down 3? Got the big down. All right. It's going to be down 3. Well, let's take a quick look on Desmos. Actually, I don't want to do that this way. Let's do it here. So if I replace this with 2 to the x minus 3, it's been shifted down 3. But notice something else that got shifted. And that is, in our original graph, wrong one, there we go. In our original graph, the one that I have here for you, y equals 2 to the x, there's a horizontal asymptote. That's some fancy vocabulary that I mentioned just a minute ago. And that is, this graph gets close to, but never really quite touches, this line right here. So that's y equals 0. That line, just like the rest of this graph, gets shifted down by 3 units. So where's that line going to be for my new graph? At -3. So let me just draw a little dashed line here as my new horizontal asymptote. 1, 2, 3. So this is not really a feature of the graph. If you look back at my Desmos graph that I had up on the board briefly, it didn't have that line, but you could see that it was headed here. It was coming close to this, but not touching it. So y equals -3. That's my graph. Let's work with this point. That's the point at 0, 1. Where's that going to be in my new graph? What will its coordinates be when I shift it down 3? 0, -2. Thank you, ladies. 0, -2. Notice that it's 3 points down. 1, 2, 3. Notice that it's just 1 point above that horizontal asymptote, just like it was up here before you shifted things. So let's try and graph this. And let's see. Something like that. Okay. you might be able to predict what's coming next. Pretty close. We'll do 2 to the x plus 4. Careful. We're recording. It's all right. Now, when you do this one, start by shifting the horizontal asymptote. And if you want to borrow a ruler, I've got some up here that you can borrow. These aren't calculators. You don't need to leave me collateral for them. Just return them if you would, please. But shift it up by 4. And see if you can't come up with what the graph should be. Well, it depends what you're shifting. If you're shifting the asymptote, then you're going to shift up 4 from 0. 1, 2, 3, 4. So it's going to be right here. Yeah. You're shifting the asymptote first, and then shift this point second, and then you should be able to draw the graph from there. Chris, something not sitting well with you? Yeah, this point is going to end up right here because you're shifting it up 4. So if you add 4 to 1, that new point will be right there at 0, 5. But you also need to graph the horizontal asymptote. That'll be the line y equals 4, yes. So here's our asymptote. And that's the line y equals 4. And then we got to draw that function passing through here and getting close to this new line. Don't get close to 0. Don't go across that. Just get close to the new line. So something, kind of like that. And again, I'm not looking for perfection. You don't have to give me perfection. How are those two looking? Those last two, those vertical shifts. Good on those? You can always check these on a graphing calculator. So if I take out my graphing calculator and I put that in here, that'd be 2 raised to the x and then plus 4. Now if I'm trying to graph this on a graphing calculator and I want to compare it to something that the instructor had, I might want to set up my window to be kind of the same that he or she has. So that'd be negative 6 or 7 to 6 or 7 on the x-axis, and then say negative 5 to 10 on the y-axis. So under your window settings, let's see if we can't mimic those. Negative 7 to 7, and negative 5 to 10. That should give us a, oops. Luca, I think this is the one that you used. All right. But we're getting the same kind of graph here that we got right here. Okay. Nice. Let's do some more here. This time you're going to get a combination of things. Y equals 2 to the x plus 2 plus 3. So there's two things happening to this, right? Good. Shift left 2 and up 3. So one of the things you should do first is figure out, well, where's my new horizontal asymptote? That line at y equals 0 is going to get shifted up, so draw that. And also keep track of what happens to this point. When I look at your graphs, the only point that I'm really going to look at carefully and closely is what happens to this point. And the rest of it, as long as you have the correct general shape, that's fine. Go ahead, try and graph it. Try and figure out what that new one looks like. looks like. Set x equal to 0, because that's the y-intercept, and the y-intercept is always going to have to go to x equals 0. Okay, so, well, let's see. What kind of a shift does the plus 2 create? Left plus 2, so 1, 2. And then what's this do? So that point that was there is now here. So we'll have shape over here. This should actually be up here at 6. Or excuse me, 7. So let's figure out a few things about this graph in terms of how it's been shifted. What's the plus 2 going to do to our graph? Left by 2. And how about the plus 3? Up by 3. So let's start with the plus 3. And I'm going to draw in a new horizontal asymptote. Yeah, this is what you were bothered by earlier. Remember that the horizontal shifts are kind of opposite what you expect. So earlier we had a plus 3 here, and instead of shifting to the right by 3, it shifted to the left by 3. And likewise, here again in the exponent, the plus causes a shift to the left by 2, and we also got a shift up by 3. So I'm going to draw my new horizontal asymptote first. So 1, 2, 3, and I'll just sketch in this here. Actually, I think I want to do it in this. 1, 2, 3. Now I draw in a dashed line to draw attention to the fact that it's not really part of the graph. If I graph this on Desmos, you wouldn't see this here. The next thing I'm going to look at is where this point goes to. This point at 0, 1 is going to go to the left by 2 and up by 3. Let's make our life a little bit easier and graph one more point. 7. Excellent. How'd you get that? Perfect. Yes. So along the y-axis, the value of x is 0. So if you want to find the y-intercept, you set x equal to 0. 0 plus 2 is 2. 2 squared is 4. 4 plus 3 is 7. So that's going to be right here. And again, from there, it's just connect the dots. So let's see if we can't do that. And that gives us something like this, just shifted up into its new position. How are we looking on that one? Okay. Now these are the kinds of shifts that I want you to know cold. These are the ones that I'm going to quiz you on the most on the exam. There are a couple other things you can do as well in working with your graph of the exponent or exponential functions. Let me just show you a couple of these things. I'm not going to be testing these hard or anything like that, but you should just be aware of different ways you can shift things. Let's take a look at y equals 2. Let's see. We'll do 2 to the negative x. We'll also do y equals negative 2 to the x. Let me write that one as well. So y equals negative 2 to the x. What do you think putting the negative in front of that 2 to the x is going to do to the graph? Yeah, it's going to flip it. Thanks, ladies. Just like what happened with our graphs of the parabolas, right? When we started putting a negative in front of it, instead of opening up, it opened down. Similar thing is going to happen here. Instead of a point at 0, 1 for this graph, y equals 2 to the x, what's it going to be with our this graph? Where's that going to be? 0, negative 1. Good. 0, negative 1. It's just going to be a mirror image. So, let's see, I'm going to kind of cheat a little bit and graph myself another point. But you should get something that looks like this. And that's our graph of y equals 2 to the negative, or negative 2 to the x. It's just reflecting down. Now there's one more graph, and again, these last two aren't going to be as important for me. But this last one here, 2 to the negative x. When I put the negative in front of this, I really reflect it around the x-axis. When I put the negative in the exponent, how do you think that's going to change this graph? Good, it's going to reflect it around the y-axis. So you're going to have a function that looks like this. And that'll be your graph of y equals 2 to the negative x. So you're just reflecting in a different way. So instead of increasing exponentially, this is decreasing exponentially. It's getting closer and closer to the x-axis as you move out towards bigger and bigger numbers along the x-axis. Okay. How are we looking on these graphs? Let me give you one more to practice and cut our teeth on. And what I want to see from you is that you guys really know your shift. Okay? So, all right. A couple people smiled at that. Good on you. 2 to the x plus 4 minus 5. And that's just going to kind of barely fit on our graph. Might actually make it a little bit bigger in order to fit it on our graph. But see if you can't come up with how this would be graphed, what I'd be looking for. I'm looking for the asymptote. I'm looking for where this point gets changed to, and the general layout of the function. Bless you. Okay, so first things first. What's the minus 5 do? How does that get shifted? Down 5. And what else? So down 5 and to the left 4. Let's start by shifting the horizontal asymptote down 5. So that's going to put the horizontal asymptote along the bottom here like this. So like that. And then I want to keep track of this point, the point at 0, 1. And as you just told me, that gets shifted down by 5, that's down here, and to the left by 4. 1, 2, 3, 4. So there. Cool. Nice. Now let's go for the bonus on this one as well. The bonus would be plotting the y-intercept. How do I find the y-intercept of any graph? Set x equal to 0. So let's do that. X, 0, y. Well, 2 to the 4th is 16. 16 minus 5 is 11. So I need to make this a little taller, right up there. And there's my extra point. And now I can just play connect the dots. So I'm going to have to just do it this way. It's just easier for me. There you go. So something like that. Beautiful, beautiful. Now, if you don't take the time to graph the y-intercept, that's not the end of the world here. I want this general shape. I want it through, or I want it coming close to this line, y equal -5, and passing through this point at -4 and -4. All right, to the left 4 and down 5, so that would be -4, -4. So those are the things that I would like to see. So 3 things from this graph. Like I said, that's kind of a bonus point. Ladies first, and then I'll get to you, Luke.
Where'd you get the -4 from?
Oh, down 4. 1, 2, 3. Down 5. Say 1, 2, 3, 4, 5. So if you start out here and you subtract 5, 1 minus 5 gives you -4 for your y coordinate. And then 4 to the left, starting out at 0, that's going to put it at -4. So -4 for x and -4 for y. Is that what you're looking for?
Yeah.
Okay. And you can just count it. I mean, you don't have to necessarily do anything really mathematical. You know it shifts down 5, so count down 5. And then to the left 4, you put your point, and then you look back and say, okay, that's -4 and -4.
So why do you do that again?
It's just a point that I want you to keep track of while you graph this. I mean, it's not a big deal, but this is kind of, what I consider the vertex of this graph
So
in some sense.
Like you can use that point and then the point like x equals 1.
Yeah, you could easily just plot points to graph these things. I'm not going to look for you to plot points. I hope you just understand how these graphs have been shifted and not really sit there and plot points. Yes, one more question. Sure. The bottom dotted lines comes from the fact that this graph has been shifted down by 5. Now our original graph, which I have right here, y equals 2 to the x, that has as its asymptote the x-axis, that is the line y equals 0. So that line, y equals 0, when I shift this graph down by 5, that line gets shifted to that line. So you're just shifting the whole thing down. Now you don't have to worry about shifting horizontally, you're just shifting that line vertically. All right? It's a great question. Thank you. Thank you both. All right. So I'm thinking you guys know your shifts pretty well. Let's take a look at some problems that involve exponential functions. And one of them is money. Money, money, money. That's a good thing about exponential functions. There's some not so nice things about exponential functions, but there's some good things as well. Let's see. Now, the formula for continuously compounded interest is actually on the front side of your handout. Let me actually go here. So on the front side of your handout, you've got this formula in the bottom right. It tells you about compound interest. And let me define some of these variables for you. A is the amount you end up with. If you wanted to be fancy and impress somebody, technically it's called the amortized value, but this is a kinder, gentler math class. So we'll just call it the amount. That's what you end up with. P is your principal. That's how much you invest initially. R is your interest rate as a decimal. T is time in years, of course. And then N is the number of times per year that interest is compounded. So typical values for N equals 4, that's quarterly. N equals 12, monthly. And this last one, I kid you not, N equals 360. Daily. Daily. Now what seems wrong with that? Yeah, there's like 5 days missing. It's like, well, wait a minute, you guys are giving yourselves a holiday? And technically, they are, but it really makes the tiniest of differences. Even if you were Bill Gates, you'd barely notice the difference. But that's no joke. N equals 360 is what they use to calculate daily compounded interest. Now, let's do a couple examples of this. And I'm going to do kind of a modified version of problem number 54. So let me kind of give you all the details for problem number 54, the relevant details. So 54. We're going to look at investing money in two different ways. So the first way, I'm going to invest $1,000 at an unrealistic 8% interest. Yeah, good luck getting that in today's climate. N equals 4. T is 10 years. And A, well, that's unknown. We don't know what A is. Let's compare that to something that compounds more often. So a different bank offers you still 8% interest. N equals 12. So now you're compounding monthly, and T equals 10. And I want to find out, well, how much money do I end up with in each of these? Okay. Well, on the exam, I will give you this formula. You have to know how to use it. So you're going to invest $1,000 for 10 years at 8% interest compounded quarterly. Let's type that all in. It's going to look like this. A equals 1,000, 1 plus 8% has to be written as a decimal. What's 8% as a decimal? 0.08. 0.08. So 0.08 divided by 4 raised to the 4 times 10 power. Now you can either type in 4 times 10 into your calculator or use 40. It's up to you. When you're typing it into your graphing calculator, you don't need to put in the times between the 1,000 and the parentheses. It understands that you're multiplying. So 1,000 times parentheses 1 plus 0.08 divided by 4 parentheses raised to the, let's just type in 40th power for convenience there. Okay. 2,208.0396. Here's an important question for you. Where should I round this? Beautiful. Why 0.04? Right. So, but what I want to salute you for is that you rounded to the nearest penny, right? We don't have units of currency that go below pennies, which is 1/100 of a dollar. So your answer should be rounded to the nearest penny. And in this case, 0.04. So it's about $2,208.04. That's how much money you should get back when you cash in your account. Now, why don't you try this one? Pretty similar, except we've got 12%, or we're going to compound interest 12 times a year instead of just 4. And we'll see if that makes a big difference or not. So 1,001 plus 0.08 divided by 12 raised to the 12 times 10 power. Or you can just type in 120 into your calculator. What's that?
We're keeping it at 64.
Say again?
Keeping it at 64 cents.
Yes. So just like the last one, we're going to round to the nearest 1/100 of a dollar, which would be 64 cents. So did it make a big difference that we got interest compounded, 12 times a year as opposed to quarterly? Are you going to really be rolling in the dough because you went to one bank versus the other? Not a huge difference. Not a lot. I mean, $11, not bad, but certainly if you drive there and back a couple times, you're wasting a couple gallons of gas. It might not even be worth it, right? It's just $11. So about 2219.64. There's an old movie called Office Space, and yeah, a couple Snickers from people who have seen that. And the big thing in that movie is these guys who work for some kind of financial institution are going to make a killing because they're going to take this little bit of interest that gets calculated, the part past the decimal point, and put it in their secret account and let the money add up, and they're going to be rolling in the dough. Well, I'll let you watch the movie to see what happens, but it doesn't turn out exactly like they expect. So, Office Space. Yeah, it's an old movie. I don't know how old, but yeah, it's got a little bit of a cult following. It surprises me every year that there's still people around that know it. It's like, oh yeah, you get a couple smiles of people that have seen it. Yeah. All right. So how are we doing on that one? Let's try one more from this section, and then we can be done. It's problem number 51. So we got a town with a population that's modeled with this equation. 3,745 times 0.93 raised to the t. And they want us to figure out, well, what's the population going to be in 6 years and 9 months? So when t is 6 years and 9 months. Well, in order to use this formula, t needs to be just in years. So how would I write 6 years, 9 months? How much of a year is 9 months? Yes, 6.75. It's 3/4 of a year, so 6.75. Now, just one other thing here before I finish calculating here. P of 0 would be the population at the date that this is started. Can anyone figure out P of 0 without actually taking out a calculator? Yeah, thank you. Because 0.93 to the 0 power is 1. And 1 times 3,745 is just 3,745. So this is your initial population. But because this number is less than 1, instead of a growing population, you're going to get a decaying population. And it's going to decay by about 7% per year. Now let's see how much is left after 6.75 years. And for that, we definitely want to do the calculator on this one. So I'll clear out this other stuff. 3,745 times 0.93 raised to the 6.75. So that calculation gives me 2294.625, et cetera, et cetera, et cetera. Can anyone see a little bit of an issue with this? Yeah, you should round, right? We don't want to chop somebody in half, right? You can't have like a partial person. So 2295 is about where we'd round it. So I'd want you to round to the closest integer in a problem like this. I don't want some mutilated people in my town. How are we looking on that one? All right, well done. For homework, try 27 through 33, 41, 45, 47, and 53 and 55. These are more compound interest formulas or interest problems. So make sure you don't skip those as you do your homework. Okay, good luck with all that.